Eigenvalue and Generalized Eigenvalue 2편의 두 번째 동영상을 올리겠습니다. 다섯 번째, Optimal Form 5. Consider following optimization problem with the variable vector phi in D vector. Maximize phi transpose A pi divided by pi transpose B pi. According to the generalized Rayleigh-Ritz quotient method, this optimization problem can be restated as maximize phi transpose A phi subject to phi transpose B pi equal 1. The Lagrangian is like this. The lambda is Lagrange multiplier pi this 편미분 transpose입니다. transpose E A phi E lambda B pi A pi lambda B pi, which is a generalized eigenvalue problem AB. The pi is eigenvector and the lambda is eigenvalue. Optimization problem in PCA, principal component analysis. In principal component analysis, PCA, if we want to project onto one vector, one-dimensional PCA of space, the problem is maximize U, vector U transpose S, subject to U transpose U equal 1. When U is projection direction and S is covariance matrix. covariance matrix를 다시 한번 공부해보면, in probability theory and statistics, covariance matrix, also known as autocovariance matrix, dispersion matrix, variance matrix, or variance covariance matrix, is a scalar matrix giving the covariance between each pair of elements of a given random vector. Any covariance matrix is symmetric and positive semi-definite, and its main diagonal contains variances. That is the covariance of each element with itself. The covariance matrix of a random vector X is typically denoted by SSX. XY random vectors, X n-dimensional vector. SSX is the matrix whose ij entry is covariance Xij, covariance Xij. XEI, XJE, XJ 이렇게 나타나요. Where operator E denotes the expected value mean of its argument. PCA, Principal Component Analysis. 이거 다 알고 있는 내용인데 그래도 한번 더 음미해 봅시다. PCA is the process of computing the principal components and using them to perform a change of basis on the data, sometimes using only the first few principal components and ignoring the rest. PCA is used in exploratory data analysis and for making predictive models. Is commonly used for dimensional reduction by projecting each data point onto only the first few principal components to obtain lower dimensional data while preserving as much of the data's variation as possible. The first principal component can equivalently be defined as a direction to maximize the balance of the project data. The ith principal component can be taken in a direction or orthogonal to the first I-1 principal components that maximize the variance of the projected data. The principal components are eigenvectors of the data covariance matrix. Thus, the principal components are often computed by eigenvalue composition of a data covariance matrix or singularity composition of the data matrix. 자, PCA로 돌아서. If you want to project onto one vector, one-dimensional PCA subspace, the problem is maximize U vector, U transpose S, U subject to U transpose U. 크기가 1이다. U is the projection direction and S is the covariance matrix. Therefore, U is the eigenvector of S with the largest eigenvalue. If we want to project onto a PCA subspace spanned by several directions, we have 이때는 several directions are trace U transpose SU, subject to U transpose U identity, where the columns U span the PCA subspace. Reconstruction in principal component analysis. PCA is the best linear projection, which has smallest reconstruction error. If you want one PCA direction, the projection is U transpose X. And the reconstruction U transpose 이게 맞지? U transpose X reconstruct U transpose. We want the error between the reconstructed data and the original data to be minimized. Original data, reconstructed data. U transpose U property is normal. Minimizing U better. So U transpose U. Therefore, U is eigenvector of the covariance matrix SSXT. The X is already centered by removing its mean. If we consider several PCA directions, that is the columns of U, the minimization of the reconstruction error is U transpose X property known, so that U equal to identity. Thus, the columns of U are the eigenvectors covariance matrix SSX transpose, where X is already centered by removing its mean. Kernel supervised PCA. Kernel SPCA supervised principal component analysis uses the following optimization problem. Maximize theta trace theta transpose KX HKY HKX theta. Subject theta transpose KX H identity matrix, where KX KIR kernel matrices over the training data and the reverse over training data respectively. KX는 트레이닝 데이터에 대한 커널 매트릭스, KY는 그 트레이닝 데이터 라벨에 대한 라벨을 나타낸다. where H는 identity 마이너스 n분의 1 1t 이 원 컬럼이죠. 1 되네. dimension is a centering matrix and the column will set of span that kernel SPCA subspace. 그럼 라그랑제란 트랜스 이게 돼요. 그 요놈은 요대로 되는데 요거는 여기서부터 시작해서 트랜스 KX 세타 T 요 세타에 대해서 편비분하면은 여기 EKX HK와 HKX 세타 두 배. 여기도 세타에 대해서는 HX KX 세타 감마 트랜스포즈 두 배. 그러면 이렇게 되죠. Which is generalized eigenvalue problem KX H KY HKX 요거하고 KX where theta and the lambda or the eigenvector eigenvalue matrices respectively. Fisher discriminant analysis FDA. FDA can be used to supervise the running classifier. Given labeled data, the classifier can find a set of ways to draw a decision boundary, classifying the data. FDA attempts to find the vector that maximizes the separation between the classes of the predicted data. Find the vector, maximize the separation between the classes of the predicted data. FDA is to maximize the distance of the project means and to minimize the projected within class variance. In FDA, Fisher criterion is maximize the 여기서 SB는 이렇게 되고 SW는 이렇게 돼요. Where W is the projection direction and the SB and SW are between and the within class scatters. Where C is the number of classes, NJ is the sample size of the J's class, XJI is the ith data point in the J's class, mu J is the mean of J's class, mu T is tether mean. 세타 J는 더블트너스 mu J 말 mu T인데 여기 W 보시면 요거 이렇게 되고 요 세타 J죠. SB 세타 J SW 시뮬레이터 세타 시그마 J는 WT 연수였어요. 여기 W According to the Rayleigh rates method, the optimization problem indication 26 can be restated as 26 restated as 됐습니다. 들어가는지는 이렇게 되고 람다에 들어가서 multiply equating derivative lambda to be zero. 이거 transpose입니다. Which is generalized eigenvalue from SB and SW. W vector, the vector W is eigenvector with the largest eigenvalue lambda. 예. 이 부분은 다음 동영상에 올리겠습니다. 감사합니다.